The floor to you. All right, welcome back, everybody. So we are moving on to the next topic of interest to us, which is data modeling and data validation. Specifically, it's going to be data modeling on denormalized data, because the data modeling on normalized data with relational tables and so on, this is all something you saw during your bachelor's course on data storage and management, right? So this is going to be about the modeling and validation of denormalized data. And we'll see that denormalized data works differently than normalized data. Not just in the way that the data models are going to look like, we will of course look into that, but also in the way that we define schemas and validates. And I was told, I think it was you, Matt, that during the exercises, some of the students asked, between well-formedness and validation, why don't we validate and why do we distinguish between well-formedness and validation for XML and JSON? Well, I hope it will make sense for you today, but basically we didn't distinguish in the case of relational tables, because in the case of a relational table, you have to start with the schema. You cannot even put any data in a relational table if you didn't first define a schema. We'll see it's completely different in the case of denormalized data sets. So where are we? This is the stack that we are building. And I will start with going through a recap of all the big principles that we have learned in the past few weeks of the semester. There are big picture lessons here. The first one is to learn from the past in the sense that there are so many things that have already been done, in particular in the realm of relational databases, the notion of syntax with CSV, the notion of a query language like SQL, the notion of indices, the notion of optimization, and so on and so on. So there are so many things we can learn to not do the same mistakes all over again. This also is a lesson to learn in the context of XML and JSON, because right now, JSON is taking over in terms of popularity, right? Back then, XML was the hype, right? All the papers in database conferences were about XML and XPath and XQuery, as I can remember 10 or 15 years ago. Now it's gone it's in terms of academia. Of course, in companies, it's different. Companies, XML is all over the place. But in academia, it's no longer a hype. And now JSON is taking over. But here's the thing. When JSON was started, for a lot of people, JSON was perceived or presented as, we don't know XML, let's throw it all away and start anew. This is a big mistake. It's a big mistake because that would be ignoring that XML is not just about the syntax itself, it's about the whole ecosystem. You have the people behind XML have solved so many problems that are more generic than just XML. For example, the idea of defining a tree-based data model for the syntax, the idea of validating the data, the idea of having navigation with XPath, the idea of having query languages, and so on, and working with denormalized data. JSON is just like XML in that respect. It would be a big mistake of starting from scratch with JSON. In fact, you can reuse plenty of the lessons that have been done with XML to accelerate the development of JSON by learning all of these lessons. So it's very important because, unfortunately, it is not everybody is aware of that, and you see a lot of things in the JSON community that are reinvented that would not have that need not have been reinvented. I think it's the correct auxiliary. Whenever you learn from the past, you can just learn so many things that it makes you faster. All right. The second thing we saw is to keep the design simple. We wanted to scale, fine. We just took a key value model. In the case of cloud storage, object storage, key value stores. This is how you scale, because then you can have billions or trillions of these, yes? Where's the catch? Oh, it's over there, the catch box.
Yeah, I wanted to ask this. I'm not sure. I know there's a third variant that's sort of popular, especially with the rise of gRPCs, or actually RPCs, which are protos. And I'm not sure how they would sort of fit in this picture, because, for example, with protos, we can also send data around and we can specify it again with, we also have schemas that they can follow and such. And I'm just trying to see, are they, because I know they're more like a sort of YAML format, but are we
So just to make sure I understand, with protos, you mean protocol buffers?
Yes.
Yes. This fits 100% in that picture. So I will also talk about that. What I really would like you to understand once I'm done with these 10 high-level principles, what I'm going to teach you in the case of denormalized data, and in particular the data modeling and validation, is actually agnostic of the technology. It doesn't matter if it's XML, if it's JSON, if it's YAML, if it's protocol buffers, if it's Parquet. We see there's plenty of other formats that are actually much more efficient. Of course, I start with XML and JSON because we start with syntax and take it to the higher level. Actually, as we will see, when you have validated the data, you can throw away the syntax and switch to protocol buffers or Parquet and have something more efficient. So it fits 100% on the picture, and I will come back on that. What's very important is that you understand that the focus is not XML or JSON. The focus is denormalized data, no matter what future syntax technologies we are going to have, right? That's the big picture. Okay. All right. So we keep the design simple with the key value model. In fact, back then when key value stores were invented, it was basically as popular as the blockchain. So everybody suddenly wanted to use key value stores all over the place, even though it wasn't actually what they needed, but key stores were a very big hype. You see how things come and go, right? I mean, now today it's like the blockchain is everywhere and artificial intelligence, but you'll see in 10 years it's going to be something else. Right. It doesn't mean that it's not going to become mainstream, you know, but the hypes just keep changing every couple of years. All right. So we keep the design simple in that way. So the logical model every week normally is much simpler than the implementation. We modularize the architecture. This is something we saw with HBase that is on top of HDFS, right? From the perspective of HBase, HDFS is just a file system. And then in terms of architecture, this is completely decoupled. So you just have multiple layers of technology that talk with each other. And every time you have upper layers and bottom layers. Some of the technology, I think it's in particular with networks people, there's a notion of northbound and southbound APIs that you talk with whichever layer is on top and whichever layer is below you. And it's very important to modularize things, because if you imagine you tried to design HBase, but you don't have HDFS. So you need to design HBase all the way to writing to the local disk. That would have been extraordinarily difficult to do. Having HDFS in the first place to start with as a layer made it much easier for HBase, because this is how you come up with the append optimized API of HDFS with log structured merge trees. All right, so we modularize the architecture. Probably as computer scientists, this is very natural to you because this is a concept that is everywhere in computer science. The fourth principle is homogeneity in the large, in the sense that when you look at the very, very high level, you want basically billions or trillions of things that if you zoom out, they all look alike. But then you want heterogeneity in the small, is that every individual object or value that you look at is going to have characteristics and peculiarities of their own, right? So this contrast between the two is very important. And it's especially important for denormalized data, because in the case of a relational table, you didn't have heterogeneity in the small, right? Every row looks alike in a relational table. Now, this is new in the context of big data. Even though it's homogeneous at large scales, if you zoom in, every single value can be totally different, right? And we'll also see that again in the context of validation. Okay, next, every time I separated the logical model from the physical model. This is super important whenever you build something. If you don't do that, you're just going to go crazy, and your users will go crazy. So you really need to have an abstract logical description and a data model of what you deal with and manipulate, and the physical implementation should be hidden. So ideally, you should separate the two, and even I'm teaching them separately, but this is the whole point, right? You separate the two. What that means in particular is that you can keep the abstract data model and swap the physical implementation for something else, right? This is called data independence, right? Exactly. Okay, this is what we are actually doing with SQL, right? With the relational model, that we had something on a single machine, and we are going to see that we can use SQL to query data on clusters, right? But this is in a few weeks from now. 7, we shard the data. That means that if the data is too big to fit on a single machine, we just partition it. There's plenty of names, right? Shard, split, block, chunk, partition, and so on. There are so many names for that depending on the technology. The idea is the same. You just cut the data into chunks that you spread all over the machines, and we'll see it's also used to batch process it later. You replicate the data. So every one of these chunks, you're not going to store it just once, but you replicate it. In the case of HBase, we don't, because it's done by GFS, right? So this is why we don't duplicate the regions. HGFS is going to duplicate the blocks. All right, so we replicate the data, multiple copies on different machines, and if possible, even in different regions with backups, then you don't lose it. Lots of cheap hardware. This is what we have in a data center. We have plenty of cheap machines that are running next to each other, and we are going to spread all of the chunks and their replicas all over the machines. And finally, the last idea that goes hand in hand with the idea of this sharding is batch processing. Batch processing is the idea that instead of dealing with very, very small tasks with the context switch every time, you take 1,000 similar tasks and do all of them at the same time, and you are going to save on the context switch. This is exactly what we actually saw with the log structures merge trees in HBase. That's exactly what's happening. In that case, the small task would be adding a key value. Well, in the case of HBase, you just wait until you have 1,000 of them, or I don't know, 10,000 of them, in order to then flush and compact. This is called batch processing. It's one, in an abstract way, this is an instance of batch processing. All right. Back then, actually, if you go to the early days before the computer science department existed, it was the mathematical and the mathematics department and electrical engineering. And when the PhD students needed to execute their programs, they needed to prepare their punch cards that they would bring to an office. Where they would actually take the punch cards and evaluate them, and then it would be the next day or 2 days later that they get the results. This was also batch processing. In fact, this is where the name comes from, right? Because you just have all the PhD students coming and putting their punch cards on top of each other on top of a pile, and then the people are going to just take a pile and then process the entire batch and prepare the outputs to give back to the students, right? So this is kind of course, today it's very different from having these offices. You can just do it on your laptop. But this is pretty much where the idea was born. And you see there's a lot of ideas that it seems that these are useless now with the evolution of technology, but then today they make sense again, right? Another example of that, yeah, I'm back to point 1, learn from the past. If you look at operating systems or the courses on operating systems, there are a lot of sections of the course that look obsolete in the way so I'm not an expert on that, but from what I understand, the way you deal with pages and so on, with the amount of memory we have today, some of the things are useless, but actually not. Because then we had the smartphones, embedded systems, where you have much less memory on small devices, and suddenly all of these concepts made sense all over again, even today, for these devices. So you see, this really never gets old, all of these concepts, and they can always be useful or used in different environments. Okay, this was my top 10 of the big ideas of big data. And now, where we are, is here we have done the storage encoding syntax. We saw the data model, and today we are actually also going to do validation. So data models and validation. So I'm going to start with something familiar, which is the relational data. You know that the syntax associated with tables, the natural one that people use, even business people, is CSV, right? So you need to understand this as the CSV, which is just text. But when you open a CSV file in a spreadsheet or in Python or I don't know what, you're going to have a logical view. You are actually going to see a table there, right? I think I already asked you, but who sees a table just looking at the CSV? Almost all of you, right? And my goal, I promised you 2 weeks ago, was that you see trees when you look at XML and JSON, right? That will be our task today. All right. So let's come back to JSON. JSON has 6 building blocks. 4 are atomic values, strings, numbers, booleans, and nulls, and 2 are structured. These are objects and arrays. The 2 that are structures, these are typically the ones you would not allow in a high normal form, in the first normal form in a relational table. So this is why we separate in that way, right? Everything atomic on one side, everything structured on the other side. What's important is that it's recursive. You can nest objects in arrays, in objects, in arrays, and so on and so on. Actually, this is why you get the tree, right, on the high level. Okay, so now let me ask you, who sees a tree here? Many of you, not all of you, I guess. So my goal is that you see a tree whenever you look at that kind of things. Well, we are going to draw the tree. I think it's just easier to do it that way. Okay, what would be the root of the tree? Yes?
Probably just an object because of the curly braces.
Yeah, exactly. That's an object. All right. What do we have below as the children? Maybe we can rotate a little bit. Somebody else. What are the children of that node object? Over there? Yes, you can throw the catch box.
And 2 atomic values, foo and bar.
Yes, exactly. So almost. So 2 values, yes, foo, the key foo and the key bar associated with an atomic value true. Not array, right? Array would not be atomic itself. But you're correct that there are 2 children. And what I did here, so let me be very precise. These are the 2 children, true and array, right? This is the value right here associated with key foo. And then we have an array here all the way, like all of that together is an array associated with key bar. Foo and bar here are only labels that I put on the edge, right? So this is a node, this is a node, this is a node. This is just a label that I put on the edge, right? So object has true as a child, labeled with foo, which is the key, and object has the array as a child, labeled with bar right there. What do we have under the array? Anybody? Yes, go ahead.
We have an object and a null value.
Yes, so we have the object and a null. You see here, the object is here and the null is right there. Okay, what do we have in the object? You see, every time it's a rare object, I need to add children. Yes, go ahead. You have the catch box. Oh, maybe I misinterpreted. Yes. Exactly, yeah. So you have foo as a string right here, and you see that's the key. So it's a label on the edge that is called foo bar. All right. This here is the tree that I draw from that JSON object. In fact, I can do that for any JSON structure, any JSON document. Who now sees a tree? Awesome. Who can do it for any JSON structure? All of you, right? It's now you know how to do it. All right. So this is great. Actually, JSON is so simple that that it's really something that can be easy to generalize. All right. So in fact, what we did now is the same thing that we did for CSV. Now we have the physical view with the syntax where you have a JSON object. It's a different one that I put this time, where we have a syntax that is just a sequence of characters. It's just text. But when you parse it, you can actually convert this to a logical view, which is a data model. In fact, this here is not just a diagram on a screen. This here, this structure that you see, is actually a structure that you will create in your memory. These are going to be memory pointers here. This is something you really put in memory. In memory, you are going to throw away the text. You parse the text and process it, then you throw away the text, and you end up with this structure. Everything that follows, the validation, the querying, the navigation, all will be done in the structure that you created in memory. It's the same thing you do when you implement a compiler. You parse your program as text, then you convert to an AST, an abstract syntax tree, then you work on the tree. It's the same idea. All right? Okay. Now, why did I keep telling you it doesn't matter if it's XML or JSON or YAML or protobufs or whatever you want? It doesn't matter because the idea is exactly the same. You can do the same thing for XML. You can also draw trees. They will look different. I will show you why XML is a bit different, but the idea is the same. You can have a tree. So you see in that case, we have the top level element, there's always exactly one. Remember, it's A, that's the top level element right here. We like, when we model XML, to add an extra node that's called the document node. It's just some additional node that we have here that we always have. Then we have the top element. And then you see two children, D and C. D is here and C is here. The attributes E equals F that we put here on the side. And here we have three children. This is right here. Then we have an element right here. Then we have the periods. And then B, the element here, B text, is itself contains the text here. Okay, who sees the tree in XML? No? All right, and we'll do on a more complex example, but this is the idea. So what's very important is that you understand that when you look at denormalized data, XML, JSON, or whatever, you can always represent it as a tree, always. Okay, now there's a few differences. It's trees in the two cases, but there are subtle differences in there. You might have noticed that in the case of JSON, the keys, so the labels, were on the edges. It means that if you look here, look at this one right there, the integer one. One doesn't know that it's in an array. It's just the number one living its life. The array here knows that it has the element 1, 2, 3. It doesn't know that it's called foo in that upper object. There would be otherwise a reverse pointer, right? So there is no notion for the array of being called foo. It doesn't know. This is what it means to have the labels on the edge. You can start here and navigate to foo to resolve the array. Once you have the array, you no longer know that it's called foo, right? That's the idea, how you think when you think in terms of JSON. In XML, it's a bit different. You notice that the names of the elements, A, C, and so on, they are on the nodes themselves. In other words, this means that this element here knows that it's called D. It's right there. You can ask, what is your name? You just look inside in the data, okay, that's D, right? This is not like JSON. That's a very important difference, that the labels are on the nodes for XML and on the edges for JSON. It has an impact, a slight impact on the way you validate JSON and XML, as we will see, but you will probably then see that it's a minor difference, right? Really between the two. It's still useful to understand it. All right. Okay. All right. So now we need to formalize things a bit, because all I did was show you that we can take a JSON document or an XML document and make a tree out of that. Well, in fact, there are people sitting in the working groups of the World Wide Web Consortium who are busy formalizing all of that and coming up with a standard and a model to actually represent XML as trees. So this is a separate standard. It's not, there is the XML standard itself that regulates the syntax. Then there is a separate standard called the XML information set, or Infoset if you want to abbreviate. A lot of people say Infoset, but this is basically what it does. It basically tells you how to formalize the tree structure of an XML document. Let's take this example and draw the tree. So the way that it works in the XML information set is that it has 11 kinds of nodes. That should be something easy for you to understand, because if you did some object-oriented programming, it's like having an abstract class, you know, or an interface, and then you have 11 implementations, and then you have polymorphism, right? So this is a way of saying that the tree is polymorphic, and then every node is one of 11 kinds. And as you know, the way that polymorphism works, it means that depending on the kind, the properties it has will be different, right? All right, but I have good news for you. We are going to only look into 4 of them that more or less correspond to what we've learned with the syntax. The rest, I think, of course, those interested and who need to dive in it later, you can always on your own look this up later. But I really don't want to overload you with things that I think are less central, right? So if we just focus on documents, elements, attributes, and characters, so text, that's more than enough for the purpose of querying. A lot of the things that you see over there, an expanding entity difference, reference, DTD, unparsed entity notation, they are almost legacy. You know, it's really some things you would have that people were using back then, maybe a few decades ago, 10, 15 years ago. But now we have more modern ways of dealing with these things. So this is why it's something that I really will not spend time on. Okay, so let's just focus on document, element, attribute, and character. And even there, you shouldn't be surprised, because when I presented XML to you 2 weeks ago, I already showed you in the syntax, the elements, the attributes, and the text, right? It's just the documents that I haven't told you about. So let's start with the documents. It's really just whatever is the root node of our tree. So everything is going to be called an information item. So we'll have the document information item, the element information item, the attribute information item, and the character or text information item. So the document information item has plenty of properties, but the most important ones are the children. It's actually going to be just the element information item in our case. It could also be, you know, if I had included them in my course, but I didn't, it could have been these two as well. But in our case, it's always one child. It's the top level element. In that case, metadata, right? So it's the element information item metadata that is the child of the document information item. And here I also put it because it's interesting. You also saw the version, the fact that that's where it comes from, right? So it's version 1.0 of XML. And it corresponds also, by the way, to the doc type, this metadata right there. Okay, now we look at the element information item. So let's do it with metadata. So the element information item metadata has different properties than the document information item. It's like polymorphism in object-oriented programming. So you see you have the local name metadata, right? The children, what are the children? When you see title and you see publisher, right? So these are two children right there. These are just pointers to other element information items. We'll look at them later, right? So this is just pointing to them. Then you have the attributes. Well, there's nothing in metadata, right? And then you have the parents, because yes, you have a back pointer actually in XML to the parent. It points back to the document information item that we saw earlier, right? Okay, who is following? Okay, now we look at the other ones, the other element information items, title and publisher. Well, the first thing you see is that the properties are the same because these are also element information items. So now title has the local name title, children text information items. So it's just this systems group right there that is within the two tags, right? The opening and the closing tags, so systems group. Then we have in the attribute property, a list of attribute information items. Two of them, language and year. These are also pointers because I will show you the properties of these on a separate slide. And the parent, it's pointing back to the element information item metadata, which is the one we saw here, right? So you already saw that now we have 3 nodes so far, and you already see the start of a tree, right? This is the root pointing to metadata. Metadata is pointing to title and publisher, and title is right there. And you see the back pointers that title is pointing back to metadata and metadata is pointing back to the document, all right? Okay, now look at publisher. The local name is publisher. The children, it's just text information item, ETH Zurich right there. The attributes, there's nothing, doesn't have any attribute there. And the parent, it's pointing back to metadata, all right? Now you might have noticed that I just said local name and you might be wondering, where is the prefix? Where is the namespace? Well, it's there. I just didn't want to overcomplicate things today. So I didn't put any namespaces in there to keep your life easy. But you imagine even with namespaces, it's easy, right? You just also have a prefix and a namespace on top of things, okay? Okay, now let's look at an attribute information item. So the attribute information item corresponding to the attribute year. So again, you have a local name. It's in no namespace because I didn't put any namespaces. The normalized value, 2022. Why normalize? It's because typically when you parse your XML documents to memory using this standard, the information set, you typically remove extra spaces. So imagine that I had a few spaces and then 2022 and then a few trading spaces. Typically, you will get rid of this extra spaces. So this is what it means to be the normalized value, right? It just gets rid of these extra spaces. Okay, and then the owner element, which is actually the parent, you could also call it parents, but it's called owner element for attributes, is the element information item title. So you see the attribute here is in the information, the element information item title. Then the other attributes, now we know how to do it, right? Language, so the name is language, the normalized value is EN right there, and it's pointing back also to title. Then we have text information items, so the properties are again different. Here we have all the characters, S, Y, S, T, E, M, S, space, G, R, O, U, P. I think that in the case of the info set, if you look at it strictly, it's creating one node for every character, right? But I didn't want to do that to you today, so I just created a single node with all the characters in there. Then the owner element is title because all this text right there, systems group, is in title. Okay, then I did the same thing with ETH Zurich with ETH space ZU RICH. Then the owner element is publisher. See, ETH Zurich is in publisher. Okay, and now I'm just assembling the whole thing because the pointers are implicit with children and owner element and parent, but this is what you get. The documents information item, metadata, publisher and title as children. Then you have the two attributes right there, some text, and here again, some text. For whom is that clear? Okay. So of course, I didn't show you all the properties. If you look at the standard, the information set, there are many more properties in there. But I showed you the, the main ID and the main properties. So what it means is you parse an XML document, then you throw the original text of the document away, and all you keep in memory is this tree structure with all the properties defined in the standard of the XML information set. We have a question over there, I think. Yeah.
Okay, so my question is, how would it change if, for instance, we wanted to make a group bold, for instance, I mean, like tag it as bold. So like that would that group would become a separate element.
Oh, do you mean what if we modify the file, or?
No, because now we have under the title we have text system group.
Yep.
And if we put group in, if we basically tagged group,
yes.
Then how would it change?
Yeah. So then what you would have if you added some, let's put it in bold, right? Open B and close B around. Then what you will have is systems as a child, right? And then some B element information item as a second child. And then you have group behind that new tag. Does it make sense?
Yeah, it does. So then the parent element title also has the order of elements?
Yes, the order is important.
Okay.
Yeah.
Thank you.
Just like in JSON arrays. Right. That's thank you for asking. So yes, indeed, you would have more structure right there. You can have intertwined text and elements, and yes, the order is very important. Okay. Any other questions? Yes, over there. There you go. Okay. So here, this is just a drawing, right? It's just a drawing. What you need to always come back to whenever you want to think about these things is the definition as properties. Imagine this is a Java class. These are the fields. And this is a Java util vector or Java list. And then it's a list of attribute information items like right there. So you see that in particular, you have one list of attributes and a separate list of children there. Right. So what you see here is only when I draw it, it's arbitrary, right? The way I put in there. You just need to know that there's a separate list of attributes. There's a separate list of children. There is no technically a specific order between the two because they are separate. However, if you look at XPath, the navigation language, it actually does introduce an order and says the attributes are first and then come the elements, when you scan through the document. Right? Okay. Any other questions? All right, let's continue then. Okay, so this is the idea of the XML information set. Now you're going to ask me, is there a JSON information set? Actually, no, I don't think anybody really did that. Why? Because it's kind of implicit. JSON is actually so simple that in order to figure out the memory representation, as soon as you understand that an array is an abstract list and that an object is an abstract map, that's pretty much it, right? Then you have strings, numbers, booleans, nulls. So this is the reason why there is no explicit JSON information set, probably because of the simplicity. But as you can imagine, XML is a bit more complex, so this is why this was actually needed, and there is a standard. Okay? Who is following? Okay. Then let's go to the next step, because so far we haven't validated anything. All we have done is looked at well-formedness. This is what we did 2 weeks ago. And now when we take a well-formed document, we were able to draw the tree, right? So what comes next is validation. You can see it as a pipeline, right? You have a text document that you check for well-formedness. If it's well-formed, you can build a tree in memory and forget about the exact text. And once you have the tree, you can go through validation. Validation, just like well-formedness, is a yes-no question, right? Is a document well-formed? Yes, no. Is a document valid? Yes, no. But there is a difference, is that we see that for validation, you need a schema, and I'll come back to that. But basically, if you represent that as a decision tree, I'm not saying there's no machine learning in my lecture. I could almost argue this is artificial intelligence, but anyway, you have is not well-formed, is well-formed, and if it is well-formed, then you can decide it is valid or it is not valid. Okay? This is how it works. It doesn't make any sense to ask if a non-well-formed document is valid or not. If a non-well-formed document, if a document is not well-formed, then you're already done. In Oxygen, who downloaded Oxygen? Some of you, okay, great. They did it extra for us, right? The Oxygen license. It's really super useful to even for future projects if you want to go through JSON or XML documents and some others. In Oxygen, you have 2 magic buttons. It changes in every version, right? But basically, the blue color is for well-formedness. If you click, it will tell you if it's well-formed or not. If it's not, it will point you to the errors. And the red one is for the validity. Right? Then you check, you say, this is my schema, please check for validity. And again, it will help you, right? So it's the 2 colors, just like in the Matrix movie, right? Either the red one or the blue one, but you can only click on the red one if you already know that the blue one succeeds. Okay. Now there is also an extra subtlety, because this is something that people tend to confuse or kind of think is the same thing. There is a subtle difference between the notion of validation and annotation. Technically, they work together. Validation in itself is normally just yes, no. It's valid, it's not valid. Annotation, however, is an extra step that you do on valid data, because imagine that you have an XML document and you have somewhere text that is a sequence of digits. And in the schema, you say you expect an integer. Then in the memory, this text 1, 2, 3, 4, 1, 2, 3, 4. Without validation, it was just text. It was the sequence of character 1, 2, 3, 4. If you know it's valid and it's an integer, why would you keep this 1, 2, 3, 4 as text? You don't, right? In that case, you replace this 1, 2, 3, 4 with an integer, potentially stored as 32 bits, right? So this is called annotation. Whenever you identify that data has a certain type after you validated it, you will throw away the text and replace it with the type value in there. This is called annotation. So you basically have the well-formed document before it was validated, and then you run the validation. If the validation succeeds, then you're authorized to convert and upgrade your document to use all of the type annotations all over the place, right? Okay, does it make sense? For whom does that make sense? Okay. So now, in terms of thinking, the idea of validation is that it's an opportunity that even if your data is semi-structured, you can still recognize patterns in your data. You could, of course, throw a lot of totally unrelated JSON documents, 1 million of them, and store them in a data lake. Nobody will oppose, right? As long as they are well-formed, that's fine. So you could have a list of 1 million JSON objects totally unrelated. That's heterogeneous. Then you don't have any schema. But what happens is that in many, many cases, you will actually recognize structures and patterns in your data. You will recognize, for example, that all of your 1 million objects, they all have a field called name, and it's always a string. So in that case, you can build a schema that says, okay, the object must have a field called name, and the value associated with it must be a string. then you can validate the documents and check that it's true for all of the million objects they validate successfully. And then what you get is still a sequence of trees, right? A collection of trees, which is the denormalized data set, but it's going to be more homogeneous. Why is it interesting that it's more homogeneous? Because you can store it more efficiently. And you named protocol buffers earlier. Protocol buffers are one way to actually do it. Because in protocol buffers, you actually do define a schema first. And when you say foo is a string, then you can actually store the whole bunch of documents more efficiently. And this is actually going in the direction of data frames, but I'll come back to that a little bit later. All right. And here's a quick example. You noticed that if you have a sequence of 1 million JSON documents that all have a field foo, you repeat the field foo all over the time. That's a waste of space, right? If you know the field is always there, then you don't even need to write it. You just know it's there and you only write the string. So you can save space in that way by validating the data. You cannot do that if you don't have a schema, because if you don't have a schema, you have to have all the fields every time. Okay, so now this is just in order to trigger your intuition of here, that's messy data. It's basically a document that would be potentially tough to validate, right? I just threw a lot of random stuff in there. See, it's an array of various things. This, however, probably itches a little bit because here you see it's an array. It all has objects. All the objects have the same field foo in here. It's always a string. 2 of them have a key called bar. This one doesn't, so it's optional. And it's always an array, and it's always an array of integers. So as a data scientist or as a database person, when I look at this, it itches. The first thing I want to do is build a schema and validate it, right? It's kind of the intuition of what you want to do. Here, maybe a bit less so, because it's more of a mess. But here, you probably see the structure in there. So this is exactly what we will study today, how to build these schemas. Who sees the structure in there, that there is more structure than here? Okay, very good. Let me check the time. Oh, it's actually almost 4. So that's good. I will stop here. Tomorrow, I'll talk about types, and I'll talk about it generically. It's not going to be tied to XML, JSON, or whatever, just a general theory of the type systems. So thank you very much. I can maybe ask you if you followed, as I always do here, if the window is still open. If you tell me, there. So thank you very much, and I'll see you tomorrow at 9 a.m. for the continuation of the lecture. Goodbye.